Next presentation, last presentation for this session, will be given by Professor Yifang Bang. We were expecting Professor Jun, but unfortunately he has some commitments in China, and so some family commitments, and so he was not able to come, but they share the presentation, so Yifang will present us the activity of ISPRS related to land coverage in the world of open source. Thank you a lot. So we will see. Now we have to check. So point cloud is not disappearing, unfortunately. What can we do now?
I'm not doing this again. Yeah.
Okay, your presentation is here. Yeah. Okay. From beginning? Yes.
Good afternoon, and thanks, Maria, for giving us the opportunity to talk about the world first high-resolution global land cover dataset. It's called GlobeLand30. Chen Jun is the chief scientist of National Geomagnetic Center of China. He's also a president of the International Society of Photogrammetry and Remote Sensing. I'm giving the presentation on his behalf. I'm chairing the ISPRS Intercommission Working Group on Global Land Cover Mapping and Services. I'm from KTH, based in Stockholm. Today I will give 4 different contents. First, provide a brief introduction, and then tell you what is a global land cover, 30 meter, and how it was made, and how reliable it is. And then I will talk about who are using it, what can it be used for, and then what are the challenges and directions. I think it has a lot of things to do with this group, FOSS4G, because for open data, we also need open source and free software that can make these updates and globally available. And also we need validation from from the global participants, and also making software for effective validation. And I've heard from Maria that you already done some validation, at least some of you, who participated in the land cover validation gaming yesterday. Some? Oh, okay, very good. I've seen some hands rising. We need more people contributing to the validation effort, so please go to the game site and game on. This is the first 30-meter resolution global land cover data. But first of all, I would like to acknowledge the USGS for providing the globally available Landsat data, launched 1972. Without the Landsat data free and open, we would not be able to make the 30-meter global land cover maps. So this was a Nature article. We wrote a short comment with Chen Jun last year, just to tell people that this is free and available. And the dataset was donated by China to the United Nations just before the climate summit last year in New York. So there are many interests, and I hope some of you would take a look and also help to develop this product. In terms of the UN post-2015 Sustainable Development Agenda, there are a lot of needs for global geospatial information, especially that is free, that is open, and also software that supports this free and open data, because we have to measure, monitor, and manage in order to have the future Earth that we wanted to have. So maps, we have many different types of maps and global elevation models, land cover, just to name a few things that are in need. So what is the land cover? It's the natural attributes on the global surface, the level 1, that is like water, build-up areas, agriculture, forests, etc. And then right now, the globally available products are only at level 1, that is like very general land cover types. But for many applications, we also need level 2 that has much more details. So there are a lot of challenges for getting this type of data set. So it's needed. We do need a lot of more data, more algorithm to support this. So global land cover, if you look at this graph, that according to the GEO Group on Earth observations, it supports all 9 different areas in terms of agriculture, health, pollution, disaster, climate, energy, etc. So it supports many key issues that we're concerned about. The European Space Agency recently started the climate change initiative, the CCI. Global land cover is also one of the essential climate variables. So there's a big need for this, and there's another Nature article 2012 also talk about global challenges need global solutions and global collaboration on many different fronts because a lot of the issues do not stop at the national borders. So what do we have currently? We have the first generation global land cover products that are produced by USGS, University of Maryland, Boston University, and also the European Space Agency, globe cover at 300 meter to 1 kilometer resolution. And at regional level, we have the European current land cover at 100 meter resolution, and at national level, China, USGS, they produce 30-meter resolutions, Sweden and some other national governments, so they have higher resolution products, but they are not globally available. And the second generation is at 30 meter due to the free availability of Landsat products. The first one was published by Hansen from University of Maryland in 2013, mainly focused on global forestry cover, its forest and its changes, gain and loss. And then the GlobeLand30 that was released last summer, a year ago. China spent 6 million euros and 4 years of a big workforce from National Survey and Mapping Bureau working on this. So they made this. And the paper was published last year, if you're interested, by Chen Jun in the special issue I co-edited in the ISPR's Journal of Photogrammetry and Remote Sensing. You can have a look at the paper and the detailed approaches, how they made it. So if you go to the website globeland30.org, you should have access to this data set globally. I just tried out earlier here, and the link works. So what is GlobeLand30? The characteristics, spatial resolution is 10 times higher than the current state of the art at 300 meter resolution. Temporal dimensions, it's 2 products from 2000 and 2010. These were derived from over 20,000 Landsat images. For each year, to have a global coverage, you need about 10,000 satellite images, Landsat images, to cover the globe. As you know, Landsat is an optical sensor that's affected by cloud cover, so it took 6 years. Before and after 2010, it's not everything is from 2010 in order to have the global coverage. So it's not an easy effort. So they collected many images and did quite a lot of work in order to produce this data set. The accuracy assessed by various third parties, I'll tell you a bit later. One was 83% overall accuracy. That's quite good. China, maybe you have heard, there's another product called from GLC. So China actually produced 2 global land cover products. You probably have heard about both. The from GLC was produced by fully automatic approach based on the same data set. That has accuracy around 67%. They just tried fully automatic approach because you want to have some good algorithms that can work on the images, automatically extract the information you want. However, the accuracy is not so high, so it's not very reliable. Therefore, Chen Jun and his group used this pixel object and knowledge-based approach. So the accuracy has improved. So some snapshots of Beijing and its surrounding regions, the change from 2010 to 2000 to 2010, the pink are urban expansion in Beijing. And Stockholm, if we zoom in, we can see the area, Stockholm shows up its archipelago, and then the city. It's quite good. And I've just added comma there, so this would be the product that you're validating if you're doing the gaming of the land cover validation game. So as I mentioned earlier, this was the paper that was published, and ISPR support open access, so this one you can read download for free. And so the idea is this is an operational product that is supposed to be reliable, can be used by many applications. It has a predefined delivery time schedule, and versus an experimental product that's like from GLC that is an experimental product. They try different classifiers using automatic approach. The accuracy may not be reliable even though they use novel algorithms and models. However, there are many challenges when you produce something like for operational use. So here, in terms of data acquisition, as I mentioned, for global coverage, it took 6 years. That only covered 74% of the globe. The rest, 26%, were from all the other years and also not from autumnal season. You would like to have maybe non-winter season for vegetation mapping, for example, and also less clouds in the image. Data processing at local scale, maybe one algorithm can do everything, but at global scale, even if you say wetland in different continents or even different regions, climate zones, they appear very different. To classify this, it's a big challenge. It requires multiple algorithms and may even expert knowledge. In terms of validation, it's a huge area. And validation is a major issue and challenge. So within my ISPR's GLC work group, we call for global contribution of independent validation of all land cover products, not only GlobeLand30. We also validate MODIS 500 and the ESA CCI land cover products as well. So the challenge itself is listed on the right-hand column, geometric radiometric reconstruction for global 30-meter imagery coverage, and also appropriate classifiers for handling spectral confusion and diversity, and accuracy assessment to ensure the reliability. So the POK approach, you have the remote sensing imageries, and then you do geometric correction and radiometric normalization or correction. And then you actually have the web-based ancillary data to help you if you have existing information, for example, OpenStreetMap or some other data you might use to help classify urban areas. If you have a big road network, etc., that can be useful. And also integration of pixel object-based approach, because different methods are required. And also knowledge-based quality control or validation. So if you have something you know with expert knowledge, that the built-up areas will not disappear generally if once it's built. Therefore, that knowledge is useful. If you have a hole in the middle of the city, it might be an error rather than some change. So maybe some more, there are a lot of details in terms of classification. I will not say everything here. So you have the per pixel, per class extraction. So the idea they made was water is the easiest to classify. They extract the water layer first, then they leave the water layer, and then they go to the wetland layer, and then snow and ice, then go to artificial cover, that's urban, then cropland and forest shrubland and all the some others, and then tundra. So these are the 10 classes they have. And in terms of a pixel-based approach, they use spectral, textual, and the multi-temporal information, a supervised classification decision tree that was used. And in terms of object-based identification, they use the multi-scale segmentation and automatic labeling and classification to generate the object-based result. And knowledge-based verification, first they have a knowledge integration platform, and there's some menu interaction and validation as well. In terms of also some quality control and other product integration. And in the end, you have the 3 methods, the pixel, the object, and the knowledge, so-called POK approach to generate this product. So I'm just going to go through this and show you some pixel-based approach. And this is a image from northern China. You have a lot of artificial small villages and then agriculture field. And then object-based approach, these are the built-up areas using a object-based approach, looking at the neighborhood rather than individual pixels and run the segmentation. Then you have these similar pixel-based and object-based comparison here. And then the knowledge-based approach, as I mentioned earlier, there are different knowledges that we humans have. The machine learning are not still good enough to perform as good as our, when we look at something, visualize it, we can quickly get the contextual information and also our knowledge about the past, etc., in order to say, okay, this is a particular land cover class. However, the machine needs a lot of rules and to learn. That is still not, we're not there yet in terms of artificial intelligence. But maybe some of you will develop this further, then we can have a knowledge-based approach that's completely machine-based. At this point, they have used a human knowledge. For example, croplands with crops, or after harvesting, they have different spectral information. If you have images that from different seasons, this would be good to know. One signature cannot represent all agriculture classes. So some examples in terms of natural knowledge. So here, is it water? Because it has similar reflectance as water, but it's actually a shadow from a cloud. So the human knowledge can do, but I think we can also train probably classifiers to recognize this as well, but we need to build, let's say, if it's in the adjacent area of a cloud, for example. And culture-based knowledge, geographic names on the left side. This area was not classified. It's in the middle desert. It's difficult to classify it, so it wasn't picked up by the classifier, but because you have the place name, then you know there's a village or town there, so then you can add this to the missing part. and knowledge-based verification of cultivated land. And in the middle of the Amazon forest, there's a clear-cut area. This was missed from agriculture, but by looking at the high-resolution images, you're able to pick up the missing part. But unfortunately, this knowledge-based approach may be not very feasible if you deal with really at a global scale. It's very time-consuming, so we need development from you, the group, how actually we can do this in a more automatic way. So then there are a lot of quality control measures has been implemented because there's a survey and mapping agency. They have the minimum mapping unit and allowable minimum errors for every class. They check and do a very good quality control for every class. Then they also called for validation from third party, because usually your own validation, as our past experience show, always have a higher accuracy than the independent validation. So this was validated by Tongji University in Shanghai. They look at 80 map sheets globally selected. If you look at where it's selected, these are the selections. And lots in Asia, only 6 map sheets in Europe, and total 150,000 pixels samples were selected. For this validation, the result shows the overall accuracy average is 83%. Water, of course, has the highest accuracy. But quite easy to classify. Maybe shrubs and grass, they are really easily confused. The low vegetation in Landsat imagery, it's not very easy to separate them. So there are confusions. So maybe they also confuse with forest. This can be solved, in my own opinion, with maybe radar and other type of images that can improve the result with the launch of Sentinel-1 that we have globally available radar satellite products. At least the synergy of fusion of SAR and optical would be very useful. So accuracy assessment done by my group in collaboration with the IRASA colleagues in Austria. So I mentioned earlier that if your own validation, for example, the MODIS, this is only for water. MODIS own validation disagreement is very little, so that means high accuracy. But we actually had volunteers using the GeoWiki system, similar to the gaming engine that you have for the land cover game. So it's actually 31% disagreement. So again, globe cover its own validation, it's less than 1% disagreement, but we found it's 18% actually disagreement, just for water. But for GlobeLand30, if you remove mixed pixels, for some of you participated in the validation of Como, mixed pixel is a big headache for everyone. So if you take away the mixed pixels, then it's less than 5%. But if you have all the mixed pixels, it's less than 6% disagreement. That's a very good accuracy at a global scale. But you can see mixed pixels. If you only evaluate mixed pixels, so they're about 50-50. Can be land, can be water. So just take a guess. So the mixed pixels are a really big headache for all kinds of validation activities. We have a lot of discussion about how to handle mixed pixels. So if you have good ideas and develop some software to handle this, that would be great. And Maria did some validation as well. This was published in remote sensing, the open source journal. So if you're interested, read the paper. And another one was done by a Greek colleague. So we have quite good validation efforts in Europe. So we need more efforts in other parts of the world. UNEP also showed some validation for the products. And in general, IISA recently published a validation of forest. GlobeLand30, it's much higher accuracy than others. So then I'll skip that. So who are using these products right now? According to the statistics by NGCC, by May, there are 5,000 users from 90 countries already, 120,000 or 1.2 million, I'm not sure, it looks strange. So a lot of map sheets were downloaded, and so big interest from different parts of the world. A lot of NGOs and UN system and research institute universities are using these products. And some application examples, for example, you can do a lot of statistics using this data set in terms of different land cover types, the percent of the cover globally. And you can also look at statistics of built-up areas and urban expansion. Built-up area, if you look at the map, and cultivated land, how that was converted to urban, and lots going on in Asia, for example. The UN projected that the urbanization in the next 20, 30 years, it will be 90% occurring in Asia and Africa. So you can use this as a base for simulation and modeling. And it can be used for peacekeeping operations, modeling, etc. So this is just to show some urban expansion simulation in different areas. Okay, so of course there are many other applications you could think of that I would skip. Yeah, some of the earthquake impact information for disaster management that is very useful. For example, for the Haiti earthquake, we were looking at right after the earthquake, within 24 hours, the Doctors Without Borders needed a map for set up field hospitals, and they were looking for information. It's very much lack of information in the disaster-prone regions. So this data would be a good base for disaster management. So what are the future directions? Definitely, we need reliable global geospatial information, advanced geospatial computing capability, and we also need geospatial analysis, open source, free software for this. And we need actually updating the global land cover map. Let's say we need a 2015 version. The product, 2010, is already 5 years old. So we need updates. We need global collaboration for this update. So if you're interested, please contact Professor Chen Jun and me. We're collecting a group of international colleagues, and we try to get a new update going as soon as possible. We also need some collaborative information services in terms of validation and also services. We would like to use some crowdsourcing using open software like GeoWiki so that people can contribute to validation and updating on this. Okay, so the idea of Chen Jun is to create a collaborative platform for global land cover information. So here you have GlobeLand30 and other global land cover data and regional country level data. That you bring all of them together and with service-oriented computing, that integrated information services that users have access. Users don't have to go to a different website to look for different information. They're all together here you can do some analysis as well. So to provide a one-stop service. So that's one of the future ideas Chen Jun has that needs collaboration from all of you. And so to set up a way to work together, there's 3 collaboration principles. One is co-design, co-development, and cooperation. We need community engagement, technological architecture, and also some governance and legal aspect to take into account as well. To end, I'm supposed to play a video for him, but the video didn't really work out. So maybe when it works, Maria, at a session tomorrow, then we can show, because now I haven't managed to make it work. Okay, so yeah, if you have any questions, yeah, contact Chen Jun or talk to me. I'll be around today and a bit tomorrow. Thank you very much.